Yeah, let's just wait a few minutes. People to trickle in. No. Yeah, let's sit around the table. So, in case there's questions.
Finally joined the table. Cheers.
You know, finally have enough seats around the table.
So, for the last 4 months, there is another data set that we haven't really used because it's too small, but it could be perfect for validation. It's the E4E data set. What we could do is we know the bird species, so we can take the bird species from the strong reach triangular pipelines, train on open soundscape, and then validate against NIPS.
Okay. But yeah, let's talk about it.
Oh, I went to
Definitely.
We don't believe in the business now. Yeah, sounds good. Just thought I'd let you know.
Stay in.
What?
Give them a call for us.
Stay in. I took it out. I'm sorry. Here.
I think it's better without it.
Better train your listeners better so you can listen to them.
Mhm. Okay, shall we get started?
Maybe we can get started. Chris, you want to step forward?
So I don't know. Can people hear me okay on Zoom?
Yes.
Okay, great. Thank you. Awesome. So welcome everyone here in person and on Zoom, and thank you for coming to this final like end of the summer presentation for our Engineer for Exploration program. I think everyone is pretty familiar with the program, but just in case, so Engineer for Exploration, or E4E, is a program here at UCSD where undergraduates work on new technologies to aid in exploration, ecology, conservation, and so they get to build new hardware and software and work on applications that actually make a real world impact, right? And that's kind of the cool part. And in doing that, they work very closely with the scientists whose work is actually impacted by these technologies, right? So they work with ecologists, biologists, archaeologists, yeah. So what we're here for is basically the end of our 10-week full-time summer program that was funded by an NSF REU side, but also by the ECE SRIP program and UCSD TRELS. So we definitely want to thank them for their support. We also would like to thank the CSE and ECE departments, HCSI and QI for their support, not just for the summer program, but also for their support during the year, because this program, Engineering for Exploration, also runs during the year for our UCSD students. So that continued support has been super valuable in kind of us being able to offer this to our students. Of course, also like to thank the scientists, right? The scientific advisors who served as inspiration, who helped the students, who provided resources and a lot of their time, right? A lot of their time and knowledge. So that support is really like what creates this program. So in the summer, we had 12 students here in person working on these projects, plus one high school student working remotely. And they worked on 4 different projects in teams, and that's what they'll be presenting on. So this is kind of a weird setup. I don't know if you can kind of see, like, we have the students here around the table, or at least some of the students. Some are joining us remotely because their semester has started, and so they have to leave us a little early. But so the program was in person. It's just really nice after having been remote and then hybrid for the last few years. But so this kind of presentation format is kind of a something that we did when we were remote, because kind of campus is still a little bit of this hybrid mode where a lot of the researchers aren't here all the time, and so we thought this is kind of a way to involve more people in these presentations. But so the format is each team prepared a 3 to 5 minute video that we will be showing, and we'll be viewing together. And then afterwards, we will open the floor for questions. So you can unmute and ask questions, or you can type questions in the chat during the video or after, and then we will get to those questions. Oh yeah, I also wanted to mention that the two people I forgot, that Nathan and Chris, who basically also provided engineering support during the summer. But yeah, so we will get started with the videos, and I think the first video is the Acoustic Species project. So yeah, enjoy, and thank you, everyone.
Soundscapes in the environment contain a vast amount of information. By listening to bird calls, you can learn what species live there, how many of that species live there, and by proxy, the health of struggling environments that may be hidden by traditional techniques of species monitoring, like camera traps and radio tracking.
At least that's the idea in theory. In 2019, scientists from the San Diego Zoo Wildlife Alliance placed 35 microphones in the Peruvian Amazon for about a month, collecting over 1,500 hours of audio.
On average, a person takes at least 3 seconds to manually label 1 second of audio, meaning it would take 4,500 hours, or 187 days, to label the full dataset. Therefore, manual labeling is a very expensive and time-consuming process.
To automate this, we can utilize recent developments in machine learning and bird classification. However, most bird classifiers are not largely trained on Amazonian species, instead focusing on Europe and North America. To use these models, we could retrain them to better identify Amazonian birds. To retrain models, you need labeled data, which we don't have since we're trying to produce it using the same ML pipelines. So, how can you retrain models with minimal human effort while maintaining quality?
Well, there is a way around this problem: publicly available data. Citizen science platforms like Xenocanto have huge repositories of audio recordings, organized by species.
However, this audio data is weakly labeled, with one species name for an entire clip. It does not tell us how often birds call, and there may be multiple species in a single recording, and that could confuse a machine learning algorithm. What we need is strongly labeled data, where the time of each individual species call is known.
However, if we use a binary detector to identify bird-like sounds, then more often than not, the sounds are the weakly labeled species. This creates a large number of moderate quality labels to train on. This summer, we worked on determining if this is a viable strategy for model training.
Before we can use the models, we need some ground truth to test their ability, meaning human labels. This is where PyroNote, our web-based manual labeling platform, comes in. To do this, we selected 10 random Amazonian species with a large number of clips on Xenocanto, with 2,000 seconds of audio sampled for each species. We then had 21 volunteers from the 2022 UCSD Cosmos machine learning cohort label this data with the weakly labeled species, or, if they were unsure, generic bird labels. In total, they created about 500 annotations per species. This data will serve as our ground truth.
Our team looked at a few well-performing bird detectors: BirdNet, Microphone, and TweetyNet. Even if they cannot classify species in remote areas well, they can still detect obvious enough examples to use to label data of birds. To classify the species, we can apply the weak label for the species, or use BirdNet to classify its known species to make more accurate labels. With this now strongly labeled data, we can train models to go from unlabeled to strongly labeled data.
These detectors can be used in combination with a classifier to create weak to strong label pipelines, or WTS. we have tested and developed the following weak to strong pipelines and apply these to all the data we have for these species. Then we can compare the labeled Cosmos sample to the weak to strong labels to evaluate our pipeline performances.
Our key evaluation metrics are precision, recall, and ROC curves. If we have higher precision, this means the model frequently correctly identifies birds. If we have higher recall, the model detects most bird calls in the clip. Finally, ROC curves give a sense of model accuracy. A model guessing at random will have a 50% chance of getting it right. An ideal model tends toward the top left corner. The higher the AUC score, or area under the curve, the better the classifier.
For the weak to strong label pipelines, we have high precision and low recall for each species of interest across the board. This means we have few false positives, but a lot of false negatives. When we train models on the weak to strong label output, this might mean data is less likely to be mislabeled, but also lead to some calls being missed. Many of our pipelines have AUC scores around 0.6 to 0.8, indicating their average classifiers. Ideally, what we want to show is our retrained models should have higher AUC scores than our weak to strong labeled models.
Now that we have pipelines to create training data, let's go ahead and train some models. We ran each of the 6 weakly to strongly labeled pipelines over all of the Xenocanto data we had for our 10 species of interest, thereby labeling tens of thousands of clips automatically. We then trained separate instances of something called Open Soundscape, an open source retrainable bioacoustic model. This way we can compare the resulting model's performance from each weakly to strongly labeled pipeline, thereby determining how good each of those pipelines are at generating high quality training data.
Once we have retrained the model, we can revisit our evaluation metrics. Here, we see that the ROC curves and AUC scores for retrained models are much better than those of the WTS pipelines. This is promising. However, our precision lowered and our recall is higher, implying the retrained model has more false positives and leaving room for future improvement.
This experiment suggests that our pipeline can train a decently performing model on data that humans have never strongly labeled, with only time taken by citizen scientists to label their clips on Xenocanto and the 1-hour session from Cosmos students. This is a significant decrease in time spent labeling versus manually labeling the entire dataset. Further, we have a model we can apply to new data, further eliminating future need for human laborers, with the exception of getting more ground truth.
To improve model accuracy, we look to improve the quality of our annotations. The following work is still in progress.
This summer, I worked on using embeddings, or numerical representations of short audio clips, outputted by an existing model to increase the precision of annotations from other models. This would allow for new training data to be stronger, due to fewer falsely identified bird calls. So far, I've used a clustering model that groups the embeddings in a multi-dimensional space. I then filtered out all of the embeddings labeled as noise. By filtering out noisy annotations, we ensure that we train on a larger amount of data that has fewer falsely identified bird calls, thereby improving the performance of training models.
Another thing we can do is get better models to ensure our ground truth is of better and better quality. Since manually validating human-labeled annotations is a slow process, it would be nice to have an automated system in PyroNote that can measure the quality of annotations produced. One way is having multiple users labeling the same clip and seeing how much they agree. If they disagree, we can have additional users label the clip so we can better identify the ground truth. This summer I experimented with pairwise agreement metrics. I tested 3 different methods: clustering annotations based on start and end, majority vote on time chunks, and using intersection over union. What I found is majority vote and intersection over union tends to give lower user agreement because they are skewed by outliers. Clustering is much more reliable at handling outliers, giving accurate user agreement metrics. Hence, clustering will be implemented into PyroNote to help us improve the quality of the data we label.
The work of the project is currently ongoing, so we still have some work to do.
We hope to make the model more accurate via BirdNet embeddings,
Retraining other models like TweetNet and BirdNet,
and utilizing user agreement methods in PyroNote to improve our ground truth.
By continuing to flesh out this methodology, we hope we can apply our models on field data this year and be able to accurately label data.
In doing so, we make it continuously easier to monitor the rapidly changing biodiversity of our planet and let these species be heard.
Great. Well done. So are there any questions? So feel free to unmute yourself and ask a question or put it in the chat.
I like the Zoom pic. Remember videos.
Yeah, those videos of pandas and stuff, that was those were not birds. That was footage from a zoo trip our student went on.
In defense, we are acoustic species.
Yeah. Not just birds, I guess.
So, the birds are just because there's a lot of data for birds. So
Yeah, so any questions at this point? Don't see any, then we can move on to the next project, and people can kind of think a little bit more about their questions. We'll have another opportunity at the end of all the presentations. So yeah, Nathan, want to start the next video?
Oftentimes, during research, ecologists need to track the position of animals within their habitat. One of the most prevalent animal tracking methods is radio telemetry, which depends on tagging animals with radio transmitting devices and then traversing the open habitat with large radio antennas like the one pictured here, following the signal from the animal's tags. However, manually searching is both time-consuming, physically exhausting, and impossible in situations where measurements are needed in frequent intervals, over long periods of time, or in inaccessible habitats, such as sharp, rocky cliff areas. This summer, E4E's radio telemetry tracking project collaborated with Dr. Matthew Gifford from the University of Central Arkansas to develop a new system that can collect location data of common collar lizards. This new system will collect position data every 10 minutes during daylight hours with a margin of error under 1 meter for the course of 2 weeks within a predefined area of rocky open habitat. Our previous system for tracking tagged animals in the field was a drone-based system. But due to the need to monitor the lizards every 10 minutes, a drone cannot be used as it would quickly run out of battery and would require lots of maintenance. In order to mitigate these issues, our existing system had to be modified. Our new system will use multiple antenna towers instead of a single drone. These will be able to run and collect results autonomously, so they don't require a pilot. Our tower systems will have a sleep timer to automate turning the towers on and off at the intervals at which data is needed to be recorded. In this video, we will outline the major areas of development for this tower system from the summer. In the previous drone system, the drone software ran on an onboard computer, OBC, and acted as a server, with the ground control station, GCS, connecting and receiving data as a client. This was problematic because for our new tower system, we want multiple towers with their own onboard computer. If they are the server, this complicates having multiple towers. So in order to implement the multiple tower system, we transitioned to a flipped TCP model. The GCS was changed to the server, and the towers acted as clients. Additionally, the existing ground control station expected one singular connection, so it needed to be updated to manage data from multiple connections. This was accomplished through the implementation of additional threads. The underlying logic also had to be expanded to utilize multiple connected data sources to display results on the user interface and allow the user to set settings for each individual connection. The next major development for our new tower system was the implementation and integration of a sleep timer. The creation of a sleep timer was necessary as we needed to conserve power since our tower system is expected to record oftenly for a long period of time. By turning off the OBC, we are able to stop data collection but also limit the amount of power our tower system uses. The main action of our sleep timer is to turn on and off the OBC when specified. In order to achieve this, we utilize an STM32 based development board and created software that can communicate with the OBC over a serial port. The sleep timer is able to interpret wake-up alarm messages sent by the OBC and turns on and off the OBC via a GPIO pin that controls a switch. The next major development was the physical design and later redesign of the tower system. The initial concept of the tower system centered around a 10-foot tall steel mast. The mast would be supported at the base by an off-the-shelf tripod and stabilized at the top by 3 guy wires. Guy wires keep the mast stable by placing the mast in the center of 3 opposing forces. However, the guy wires must all be in tension for them to properly exert force on the mast. This became an issue when we realized that it would be extremely difficult to anchor the guy wires into bedrock without causing permanent changes to the ground. To solve this issue, we redesigned the tower system and switched to a tree-mounted design. This design will work in the area of interest for this deployment, since the habitats of interest are all surrounded by trees. The tree mount consists of 7 sections of PVC pipe connected by PVC angles. The antenna then sits within the PVC pipe, protecting the antenna. The entire assembly is strapped onto the tree with ratchet straps, allowing for a simple and easily removable system.
Awesome. Okay, so that was the radio call tracker project. Yeah, well done. So any questions there for our students? So we will move on to the next one. So now we'll be moving to underwater stuff.
The ocean is the most important part of the Earth's ecosystem. It absorbs up to 90% of the heat from global warming and produces over half of our oxygen. While we have a lot of data about rising ocean sea levels and temperatures, scientists have a lack of nearshore data, which would allow them to better understand how these changes affect nearshore ecosystems. Whereas in the open ocean, researchers can put a buoy or use satellite data to track ocean conditions, the dynamic nature of changing coastlines make it almost impossible to do the same for nearshore data. However, this nearshore data of interest is exactly where surfers go every single day.
The Smartfin acts just like a normal fin, but is a platform for instruments that you would find on NOAA buoys. Smartfin collects motion, location, time, and temperature data, and with this information, researchers can track temperature trends over time, as well as use motion data to learn more about wave patterns. Here is data collected at Windansea Beach during a longboarding session in July. We can see the fin adjusting to ocean's temperature and giving us data accurate to 0.1 degrees Celsius when it was calibrated. We can also see spikes in acceleration here and here, showing certain waves that I was riding, or times when I wiped out. Combining the 9 axes of movement, we can discern position and maximum velocity of a surfer on a wave, which can lead us to calculate the minimum wave height to produce those effects. Surfers can treat the Smartfin like a normal fin other than charging, making it easy for anyone to get involved in the Smartfin project.
This summer we have made several improvements to the system behind the Smartfin. An early problem we ran into was our inability to use the 3G fins. Since the fins relied on cellular networks to transmit data, our 3G fins were stuck in an upload state because wireless carriers have phased out their 3G. In order to solve this, we implemented setting a no upload flag. The fin would loop between its sleep state and charge state continuously even when water was detected. After fixing these 2 critical issues, we had a fin that was working mostly as expected. For the rest of the summer, we continued to fix bugs and add features to improve the fin.
To make sure that the fin gives accurate data, we need to make sure that all sensors aboard the fin are calibrated, most notably the accelerometer, the magnetometer, the gyroscope, and the thermal sensor. We can use the magnetometer to give us the orientation of the fin at a given time, since it measures the strength of the Earth's magnetic field in all 3 dimensions. However, before we can get reliable fin direction and orientation, we need to ensure that the magnetometer doesn't read a distorted magnetic field by calibrating it. We can offset the effect of nearby magnetic fields, such as those induced by electrical currents, and the effect of nearby ferrous material with corresponding transformation matrices. The calibrated readings were measured against video footage of a surf session and manually compared against a known calibrated compass. This is a typical surf session visualized on a compass, where the radial axis represents time in seconds.
The accelerometer is used to measure the acceleration along all three axes. Since the accelerometer can measure gravitational acceleration, to calibrate the accelerometer, the sensor was lined up in all 6 orientations and calibrated against the 1G vectors that were expected. The gyroscope measures the angular velocity along all 3 axes. There was no viable way to calibrate the scale of the gyroscope, so it was 0 calibrated. This type of calibration shows a 0 reading when the sensor is not rotating.
To calibrate the temperature sensor, we put the fin in 3 different temperatures of water within the range people can surf. The fin reading is then compared to the temperature reading from an NIST calibrated SPE, the same model used on piers across California, including on Scripps Pier. By then running a linear regression of the relationship between the true temperatures and the fin's reading, we can determine and calculate the coefficients to be able to adjust the temperature. We needed a way to pot our electronics in a fin strong enough to withstand the forces of surfing using materials found in any lab. We decided we would make a core to house our electronics and then fiberglass that core for strength. This method allowed us to make a strong, responsive, and watertight fin that surfers would love. We start with a 3D model to house all of our electronics to act as our core. We then make a mold of an existing fin. We use silicone to model the bottom and top, and this will act to finish our final fin in the right shape. Fiberglass cloth can be easily cut to any shape, and when combined with resin, creates a very strong material. We used about 5 layers of fiberglass on either side, though we hope to use at least 15 in the future to make it way stronger. Here we can see the fiberglass in the mold holding the shape of the fin. Fiberglass cloth also allows you to push the pins through so that we can access them from the outside. In our next iteration, we're going to use a larger 3D core and 10 more layers of fiberglass on either side, as well as cure the fin in positive pressure to get rid of voids in the mold. This summer, we've put a lot of time and effort into documentation and simplifying the onboarding process as well as our tools and other pieces of our code base. We hope that these efforts can help new researchers more easily contribute to the project.
Well, that was the Smartfin team presenting on their project for the summer.
Can I ask a question?
Yeah, of course.
I'm just curious what, hello, and really nice work. Great to see. What would you have considered the biggest challenge that you had to overcome?
Rob, you want to answer that?
Yeah, I would say one of the biggest challenges was, well, from the beginning, getting used to the system, and it's a pretty complicated system overall, and it's changed hands a lot of times. So, but once we got our hands on it, I would say one of the biggest issues we ran into was being able to deal with those old fins getting phased out. That's a problem that was really out of our control. 3G fins no longer working with the cellular network. So one of the big overhauls in the beginning was being able to download the data, which actually then in the end ended up really helping us out and being able to run tests faster. So it was one of those things, once it was a tough problem to deal with, phasing out of the old technology that we had, but then it actually provided us some opportunities to be able to end up making some better developer tools and testing tools for us later and get the data faster. So that was probably the biggest issue that we faced this summer.
Cool, thanks. And really nice work with the documentation too. I know it's easy to get buried in the actual engineering side, but the documentation will go a long way.
Definitely.
Awesome. Yeah, so if there are no more questions at this point, then we'll go to the last video.
Fish are hard to track. The current system for estimating fish population and health involves a diver noting the number of fish and their relative size over a specified period of time. This method, while frequently used, involves excessive manpower, provides inaccurate size estimates, and is subject to diver error.
We at FishSense hope to simplify this process with an underwater camera that can automatically identify fish and their length using artificial intelligence. Our current model is functional underwater at a depth of up to 300 feet and has been deployed with reef divers in Florida. This summer, we also implemented FishSense onboard boats for fisheries research.
However, there are multiple areas that could be improved to help the FishSense make the most accurate measurements possible. This summer, we focused on improving the artificial intelligence algorithm to better detect fish, calibrating the depth cameras for an underwater environment to improve the length estimates, and implementing hardware adjustments requested by the reef divers.
At the start of the summer, our algorithm could detect fish, head, and tail with limited accuracy. The model struggled further with retrieving precise length measurements. Segmentation, or determining exactly where the fish starts and ends, is essential for calculating accurate length. While some previous methods, such as depth-based segmentation, have achieved decent accuracy, this method is computationally expensive and performance drops significantly when we test underwater. This summer, we explored UNIT as an alternate algorithm for segmentation. Unlike the previous segmentation algorithms that have been implemented, UNIT is actually a separate convolutional network. This framework is extremely popular in image processing for its fast and accurate segmentation results.
In order for the AI to measure length correctly, our cameras also need to accurately find the depth at each pixel. While our cameras work well in air, the different index of refraction of seawater and worse contrast underwater create a depth error of 20 to 30%. In an attempt to solve this problem, we tested 5 different forms of calibration to see how they would work underwater. These methods were targeted calibration, target-less calibration, scale calibration, hybrid calibration, and copy calibration from an Intel underwater camera. Of these methods, only 3 were successfully able to complete calibration because of the difficulty of finding the target in an underwater environment. The first, targetless calibration, had a depth percent error of around 2%, but a scaling percent error of 26%. This means that it was able to accurately predict distance from the camera to an object, but couldn't find the lengths of those objects. Scaled calibration, on the other hand, performed poorly at finding depth with an error of 27%, but had a scale error of less than 1%. This means that it was able to find length very accurately, but had a hard time finding distance to objects. We predicted that hybrid calibration, which combined the two, would solve this issue, but it actually performed poorly in both categories, with a 27.5% error for depth and an 8.4% error for scale. Copying the calibration table of the underwater camera directly onto another camera made unusable results.
In addition to providing accurate measurement, our product must be usable for the divers. Following the field deployments in Florida, we've been focusing on upgrading the FishSense hardware based on the first-hand feedback provided by our collaborators. Divers had trouble using the magnetic recording switch as it interacted with their metallic gear. Therefore, this summer we have replaced it with a simple turn switch. We've also streamlined the recording light to display in a more intuitive and easily understood way, and moved it to the rear end cap of the FishSense where it is more easily visible. A depth sensor has also been integrated into the hardware, providing users with valuable depth, pressure, and temperature data from their dive. Final improvements include a real-time clock, which will provide accurate timestamps for all recordings, and the addition of a pressure valve to prevent damages caused by environmental changes. With these additions to the FishSense hardware, we further strive to ensure it is an effective and user-friendly tool for research.
This summer, we also brought FishSense on-board research vessels to help with above-water fish measurements. Fishery research groups like the California Collaborative Fisheries Research Program, or CCFRP, measure fish like these to advise fisheries management and evaluate the performance of marine protected areas.
The current process works like this. A scientist will take a fish to be measured, line up its nose with the front of a measuring board, and then calculate both the fork length, which is the length from the nose to the inside of the tail, and total length, which is the total length of the fish from the nose to the end of the tail. They also check for fish species type and their physical condition. They will then sterilize and tag the fish so it can be identified again and send it back to sea.
To seamlessly integrate our camera with the current process, we built a boat rig that holds the camera above the measuring board, allowing us to capture data as the scientists do their own measurements.
Measuring fish on boats presents a very different set of challenges than those of measuring underwater. Compared to their underwater counterparts, fish captured through on-deck videos are easily differentiable from their backgrounds and will usually be in a fairly clear position to be captured by the camera. To account for these differences, we decided to shift to developing two separate models, one for on deck and one for underwater. Since we had the opportunity to collect data on deck with our collaborators this summer, our work focused on that model. In order to integrate our system into the researchers' current work, however, we had to overcome the issue of hands obstructing the data. This issue is especially concerning considering some of the data we hope to collect is that of fish volume. With obstructions, this is virtually impossible. Thus, we developed a new protocol by which our researchers capture their data. Using this new protocol, we were able to collect the front and rear halves of the fish separately and stitch them together to then be used for calculations. This allows us to overcome the challenge of obstructions and now calculate fish length and eventually volumetric data as a part of our future work.
Eventually, we hope that our camera will replace the measuring process altogether, so scientists could just point the camera at the fish before sending it back into the ocean. This would minimize the amount of time that fish spend out of the water during measurements, which could decrease mortality rates and simplify the measuring process.
Thanks for watching. Before you go, we would like to acknowledge the team members and collaborators that made this summer possible.
Tell me why our head detection isn't great. Tell me why our depth camera won't calibrate. Tell me why collaborators only say, give us the fish length.
Well done, well done. Yeah. Good, good.
It's weird. Someone in the chat said, wow, American Idol watch.
Yeah. Yes, we know where we're gonna submit these videos. Okay. Any questions for the team here on this project? Or see if they want to do a live rendition of the song?
Yeah, there's a lot you guys haven't heard of this song.
So,
So there was the question in the chat. You wanna?
so yeah, the question is, so the upshot, underwater calibration still isn't there yet.
Not there yet, but we've tested all the methods that Intel provides as part of its system. So now we're looking more into custom calibration or the OEM calibration, which will be more difficult, but yes, not there yet.
Guys, that was awesome. Thank you so much for all the help this summer. Another question on the calibration. The video, is that for calibrating in freshwater or in saltwater, or where are we at with that?
That's a great question. So we've done all our calibrations in freshwater. We tried to test in a saltwater tank just the other day, but it wasn't deep enough, so we weren't able to get valuable data from it. But ideally, we test it in freshwater. If we find a model that works, then we can bring it to saltwater and see how different that process is. So if it'd be nicer to calibrate in freshwater and then use it in saltwater, but we don't know yet if there's going to be a difference that's large enough. That means that we have to calibrate in saltwater for it to work in saltwater. Does that make sense?
Awesome.
Yeah.
So Christy is asking, is the sense that it will eventually work well once you figure out the calibration?
There are other things that we need to fix with machine learning as well. Maybe Bella can talk more about that, but depth calibration is important because if we know the accurate calibration, like the accurate depth at each pixel, then we're better able to find the length, even if the fish is tilted or at different angles and such. But we also need to accurately detect the fish, and that's, I think, still in the process. I don't know, Bella, do you have any?
But it's more so for the underwater stuff than the on the boat stuff, right?
Yeah, on boat we're fine in terms of calibration. We're looking at improving the underwater calibration. Right now it's not as great as it can be. I think it was 20 to 30% error for detecting objects.
obviously Intel was able to do the calibration somehow.
Yeah,
So we
it
know,
exists.
we know the method exists.
But we don't know how they did it. They don't do it for us anymore. I think the system is, or the team has been dissolved that worked on the RealSense cameras. So we don't have them as a resource anymore, but we're looking at, which is why we're looking at ways of doing it on our own. But it seems like the Intel tools that they provide aren't very helpful in terms of accuracy. Any other questions?
Awesome. Or any questions for any of the other teams, or any of the other projects? So, okay.
So Chris is asking, once we figure out the calibration, will we be able to go back and rectify old data?
It's a great question. I think it depends on the data. I haven't seen the data from our latest dives, and the data that we have from our Florida dive seems all right. Possibly, I guess is the answer. I'm not entirely sure.
Well, they replied, and thank you, great video.
Thank you guys. We're very grateful.
Yeah. So yeah, thank you again, all the collaborators who supported us throughout the summer. That was really awesome, and I'm sure that really added to the experience that the students had doing this research. So yeah, and thank you all for coming to these presentations. As I said, this was the end of an amazing summer. It was great to be back in person. It's great to have all these students here working on these projects. And yeah, E4E will continue during the year, so we'll resume in fall. And I guess there's still some loose ends to tie up from this summer. But so yeah, we'll continue working on these projects. We'll continue working with all of you. And of course, if you have any new problems, you can always bring it to E4E. I don't know if Ryan is still here, and if he wants to say a few things.
I don't think Ryan's here.
Okay, but yeah, thank you again, and to all the students who are on this call, thank you so much for being part of this. It was really awesome, and yeah, to everyone, have a great rest of your summer. Thank you.
Thank you.
Great. Well done. Awesome videos.
Thanks.
I'm glad we kept that video to the end. the right way to like
Good job.
Finish it up, yeah.
finish that up. It was not what I was expecting. And I'm so
Because it was better.
and I'm so glad I didn't do a little down. I stand by my choice.
Yeah.